online seminars of the International EPR Society. I'm excited to introduce today Ciarán, the Irish way, no, the English way of the Irish name, who is about to introduce to us the modeling conformation flexibility in a spectrally addressable molecular multi-qubit model system. Now, to be honest, I was initially a little bit confused, so I tried to read up on it, and it's actually pretty interesting that one can use the conformational exchange to model the relaxation, which is induced by the two, the spin centers. So I'm excited to hear more about it. So Ciarán, why don't you give it up and fire away?
Lovely, thank you. Yeah, so today I'm going to be talking about looking at modeling conformational flexibility in this spectrally addressable model system that we've made up of multiple qubit centers. So yeah, I'm Ciarán, and I'm a final year PhD student at the University of Manchester. And this work that I'm going to be talking about was recently published in Angevante here, so you can check that out as well if you're interested. So I thought I'd just do a quick little background on me, because I always like it when other people do these things. So I did my undergraduate at Trinity College Dublin in Ireland, and I did some research placements and an Erasmus in France. Took a little bit of time at Pfizer, didn't like it too much, came back to do a PhD here at Manchester with Drs. Alice Bowen and Drs. Louise Natrajan. This is not what Manchester normally looks like. It's normally a lot rainier. And we have the EPSRC National Service for EPR spectroscopy here, where we have access to CW EPR and all these bands, some pulsed EPR, SX and Q. And very, very recently, what I've been working on is getting the light-induced EPR setup going here in Manchester. I also recently did a placement with Daniela Goldfarb at the Weizmann Institute back in March this year. So that's sort of my background and where I've sort of led up to sort of briefly. So yeah, I'm going to be talking about looking at conformational flexibility in these multi-qubit systems. So the whole underpinning theme of this is quantum information processing, and quantum information processing there's lots of different sort of areas of it, but what I'm looking at are dipolar coupled spin systems and their potential to be used as molecular qubits. So what's a qubit really? So it's the quantum analog of a classical bit. So when you have a bit for classical computing, you can be in a state that's either 0 or 1, and this is what does all your computational all your computational algorithms are run based on these bits. But with a qubit, you can be in a superposition of these states, and we can actually use pulse CPR to do ensemble measurements of these qubits. So this is sort of a basic sort of EPR setup where we have our microwave sources, which allow us to put our qubits into any arbitrary superposition of states, and then we can basically detect that using our normal EPR setup. So when I talk about molecular qubits, what do I mean? What do they look like? So there's been a couple of molecular spin qubit molecules, electron spin molecular qubit molecules suggested, ranging from these multi-metallic clusters to these sort of nuclear spin free environments around these sort of copper or vanadium and vanadal type porphyrins or phthalocyanines. But basically, I'm looking at dipolar coupled spins. So if you can and we can use those to our advantage, so we can have a look at that in a little bit. And we're also going to have some sort of diamagnetic chemical scaffold, so some type of organic linker that's going to be joining our two spin qubits, and is actually going to be the main thing that determines the interaction between those spin qubits as well. So in terms of two spin molecular qubit systems that have already been introduced, and a couple of new ones have come out in recent years, systems such as these copper porphyrins covalently linked to these titanium centers were recently published in JAX by Dana Friedman's group, and they were looking at the effects of decoherence on these two spin systems, and how much having these two different spectroscopically addressable qubits can affect. There's also been fully organic systems like this bis nitroxide compound, where independent addressability of the nitroxides was able to be measured. They were able to do independent addressability of the nitroxide, should I say, in an aligned single crystal matrix. From our group, we spend a lot of time looking at these chromium-7 nickel rings as qubits, and these can be brought together quite easily and combined with other sort of qubit centers, such as this nitroxide here. And it's already been shown that some elementary gate operations between chromium-7 nickel rings can actually be achieved, especially in aligned crystal matrices. So just to delve into the sort of chromium-7 nickel rings a little bit more, because that might be one that not many people have really encountered before. So these are these 8 atoms, 7 chromium ions and 1 nickel ion that are antiferromagnetically coupled to give a spin-half ground state. They have tunable coherence times, so we can change the ligands. So normally this pavalic acids bringing the rings together, and we can change those out and tune our coherence times based on that, for example. And these have good phase memory times compared to some of the other sort of molecular qubits that have been proposed. And the nicest thing about them is that can be really easily brought together into entangled arrays of qubits. So we can bring together lots of rings into one system, making these really big multi-metallics supermolecules that are all have interesting properties when we're looking at quantum information processing. So they're quite in terms of multi-qubit systems where we're looking at more than 2 qubit centers. When we have more than 2 qubit centers, we're looking at allowing more exotic functionalities and more functionalities that will actually be useful for quantum computing. And these include things such as quantum error correction and quantum simulation algorithms. But this has mostly been confined to the realm of sort of quantum dots and superconducting circuits where you're operating at really, really low temperatures, which is quite hard to do, quite hard to hold those temperatures. And it's quite expensive as well, especially in an economy where helium is sort of limited. But Google did this recently with this Sycamore processor, which is a 53 10,000 years, only take 200 seconds. But tuning the interqubit interaction in these sort of superconducting circuits is really quite challenging. Whereas as chemists, we can actually tune those interactions really quite easily. So we designed this model multi-qubit system. And basically we just took all the tools we had from building these rings before, from basic synthetic chemistry, and brought together sort of qubits in an arrangement that we wanted. So we wanted a simple 2-level qubit. So we wanted 3 different spin half states. We wanted to ensure factorized eigenstates of each of these so that they're not overlapping, they're spectrally addressable, and we can factorize their eigenstates. And we also wanted these interactions to be switchable. So we wanted to be able to say, well, do we want to target both 2 interactions, 3 interaction, 1 interaction? So we wanted that in our molecule as well. And with synthetic chemistry, we can do that. We can just decide how we want to build our system to do these. So we built this 3-qubit system composed of a copper porphyrin that's linked this along this thread to the end to a nitroxide, around which these has been templated. And we were able to do the CW of those at X-band, and you could see from the simulations, we could see that there was no exchange coupling. So the only interaction here between the qubit centers is going to be the through space or the dipolar interaction. At Q-band, if we look at the echo-detected field swept spectrum, you can see that the spins are completely spectrally addressable. They're completely separated. So we have in red here our copper signal, we have the blue as our nitroxide, and then at quite a low G value is our chromium-7 nickel ring. And in terms of switchable interactions, what we have is a really high disparity in T1, or the longitudinal relaxation of the spins. So it goes quite high. The T1 for the nitroxide, and this is at 3 Kelvin, relaxes the slowest, followed by the copper, and followed by the very, very quick longitudinal relaxation of the chromium-7 nickel ring. So already we have a handle here on maybe some things that we could do. And one of the things we want to do first, obviously we have 3 spin half centers that are dipolar coupled. One of the things we can look at is doing pulse dipolar spectroscopy to figure out what the strengths and the spread of those interqubit magnetic interactions are. And it will also tell us things like the 2-qubit gate times when we want to do some sort of quantum gate operations. But because it's a molecule and it's made up of these organic linkers, we need to be reasonable on how we look at these interactions and think about how much flexibility is going on there, how this is going to affect basically the how entangled our qubits might be eventually when we do our quantum operations, and how spread that interqubit interaction is. So what we did first, instead of just doing DEAR and analyzing it orientationally independently, we did a model-based orientation analysis of the 3-spin system, where we took both DFT spin density calculations combined with single crystal XRD combined with a dihedral bond angle analysis of the dihedral angles in the molecule to build this model of where our spins would be expected to turn up in space relative to each other. And what we could do is basically build a library of compounds based on all these different combinations of where our spins could end up. And that's our simulated library. And then we can get our experimental data and fit our simulated library to our experimental data to figure out where our qubit topic handle for pulse CPR. So we can do relaxation-induced dipolar modulation enhancement experiments, which is this somewhat scary looking pulse sequence, but it just breaks down to a Han echo detection sequence followed by this T mixing block, which basically replaces your pump pulse in a DEAR experiment. It allows your spins, your faster relaxing spins to relax, and then that's refocused. So it's a single frequency technique that relies on a fast relaxing spin to relax, modulating your detection spin echo. And if we look at this at 3 Kelvin and choose a T mixing block time that allows the chromium-7 nickel ring to relax, we can actually sit on the copper and oxide's barely relaxed any of its T1 within T-mix. And because we're spectroscopically addressable, when we're sitting on the copper, we don't have to take into account that we're also taking in some of the nitroxide spin echo. So we can selectively look at the copper chromium-7 nickel ring interaction solely based on the T1 or the longitudinal relaxation dynamics. And we get at these nice rhythmic traces looking at both, so obviously we're doing an orientational analysis of this, so we could look at both the GXY component of the copper and the GZ component of the copper. And you can see that when we're looking at the GXY, which is the pink trace here, we get these higher frequency contributions to the trace, which we don't see in fits. We can actually go back to our model, see which orientation is giving us these best fits. And we were actually able to corroborate single crystal EPR studies of the chromium-7 nickel rings G matrix orientation, in particular the GZ component, which is represented by these blue arrows, which have been suggested by single crystal NMR to be perpendicular to the plane of the ring. So that was really quite nice. But obviously we have 3 spin centers in there, and we wanted to look at doing RHMI of multiple spin centers. And basically we could look at sort of playing around with both the temperature and this mixing block time in order to choose which interaction we wanted to see. So to find excited states of the chromium-7 nickel ring. So we can choose these different temperatures and allow spin addressability based on how we choose our mixing block time and our temperatures. And what we saw was that at very low temperatures, where we have the ring signal quite present in the field swept spectrum, and we're detecting on the nitroxide with a short T-mix time, because the chromium-7 nickel ring relaxes very, very fast, we get the dipolar interaction expected for the distance between the nitroxide and the chromium-7 nickel ring. And again, we could fit that using our orientation dependent model and work out where our ring is ending up relative to our nitroxide spin. But if we raise the temperature a little bit and we make our mixing block time even longer, we actually start to get contributions from the copper spin coming into play. And at 6 Kelvin, we get solely a contribution from the copper spin at a very long T mixing block time. So basically, we can just change the length of our RHYTHMIA experiment and play around with the temperature as well to basically choose which interaction we want to look at. So we can look at either the interqubit interaction between the nitroxide and the chromium-7 nickel ring, or the interqubit interaction between the nitroxide and the copper. And again, we could model based on our simulation library where that copper spin is going to end up relative to our nitroxide spin when we're detecting here in our RHYTHMIA experiments. So that's all nice. So we sort of fully defined the system now, and we see that we have all to get the different interactions out. We know what our 2-qubit gate times are. So now we want to have a quick look at what we can do in terms of EPR-based quantum information processing. And two of the main things, especially looked at in our group, are quantum error correction and the quantum simulation of decoherence. So it's already been shown recently in our group that if we have a chromium-7 nickel ring exchange coupled to a copper, which also has a nuclear spin. So we have our spin half of our chromium-7 nickel ring, our spin half of our copper, and then our nuclear spin 3/2 of our copper. That can be been shown recently by our group, and this was published in JAX a few months ago, that we can probe the simulation of decoherence on an entangled state of these chromium-7 nickel rings. So we can, and I'll describe this in the next slide, but we can look at how these copper spins, so the blue are copper and the green are rings, how these copper spins can cause decoherence of the chromium-7 nickel ring entangled state. And this was shown as how much error in a quantum teleportation experiment actually evolved over time. So in terms of looking at the quantum simulation of decoherence in this 3-spin system, basically the idea is to prepare an initial entangled state of the copper spin and the nitroxide spin. And this can be done by doing a single qubit rotation or a Hadamard gate on our spin system, followed by a C0 gate, which only changes the spin state of the spin depending on the first spin state to give this entangled bell pair of our logical qubits, which will be our copper and nitroxide. We can then do a single qubit rotation of the ancilla, which in this case will be our chromium-7 nickel ring, because this is the spin that relaxes very, very fast. So this is going to be the spin that actually simulates the decoherence on the entangled states of the copper and the nitroxide. And the angle that we of the rotation of this spin is going to control the decoherence values that we actually want to simulate in this system. And then if we generate an entangling gate between the ancilla and the entangled qubits using this Toffoli gate, and then just simply wait for the longitudinal relaxation of the chromium-7 nickel ring, we can read out how the chromium-7 nickel ring contributes to the decoherence of the entangled state of the copper and the nitroxide. That's nice and all. And the things that work nicely, as I've said, is that we have operational gate times that are reasonable compared to our pulse lengths and compared to the coherence that we have. And we have this really nice disparity in T1, which allows in this dipolar coupled system, the potential quantum simulation of decoherence. But there's a lot of things that we need to make this actually work. So one of the things are the bandwidth requirements of the resonator or in our EPR spectrometer. But recently, there's been a lot of work going into these quantum electrodynamic circuits, which should allow optimal control pulse shaping. We know exactly where what our pulses are going to do and where it's all going to end up. And if there's any issue in terms of the interaction strengths, whether we need something to be slightly stronger or slightly weaker, we're really well placed with molecules to use synthetic chemistry just to change how these linkers are formed together. And we can look at the dipolar spectroscopy to make sure that everything's still ending up in the same place. And we can tune those interactions way easier than they're able to tune these interactions in these superconducting circuits. So to conclude, there's sort of two parts. On the pulse dipolar spectroscopy side, we were able to do these highly orientation selective copper chromium 7 nickel ring RHYTHMI interactions, and be able to measure those for the first time. We were able to look at both the orientation and the spin density distribution of 3 spin centers relative to each other, and side of things, we have a model here that should be able to probe the controlled simulated decoherence of entangled states of the copper and the nitroxide spin by using the fast relaxation of the ancillary spin, in this case, the chromium 7 nickel ring. And hopefully it will guide sort of synthetic development in these molecular spin qubits, looking at frequency addressable or spectrally addressable molecular multi-qubit candidates for future quantum computation and simulation routines. So that's most of what I wanted to talk about today. So there's a couple of people to thank, mainly the Bone Group and Alice Bone, who's helped with a lot of this. The Department of Chemistry here, so there's been a lot of collaboration with Richard Wimpenny and Deepak Astana, who's over in, has an associate professor in India now. The Ciarán Group, we're pictured here on the right. The Photon Science Institute, without Adam Brookfield in the national facility, I don't think anything would get done. And then the theoretical side in collaboration with the University of Parma. And all of this code that I use to analyze the data, to model everything, the orientation dependent code is all available at this on GitHub, and all the raw data is available there as well. So if you ever want to play around with it or try to do some modeling of your own,
All right. I think we lost you a couple of times due to the internet connection, but otherwise, a good job.
Sorry.
Thank you very much. It's okay. Thank you very much for presenting. And now we come to the most exciting part, which is asking questions.
Yeah.
So I will give probably like a minute or so for others to type, or just raise your hand, or just speak up, dear God. Just speak up and ask a question. In the meantime, while waiting, oh, never mind. Maxime is already asking. Go ahead.
Hello, everybody. I apologize. This laptop does not have camera. It's not that I'm so shy. Maybe it was spoken, but during these gaps where I could not hear also the presentation about this, what was it, chromium. There are 7 atoms, you say, in the cluster.
Mm-hmm.
When can you please tell quickly what is the magnetic state of this, and if you consider this cluster as a one-spin species or not? This would be first question.
Yes, so that's 7 chromium ions, and 1 nickel ion, and it has a spin half ground state at cryogenic temperatures, so below about 4 Kelvin, and this 1 electron spin is delocalized over the ring.
Okay, so it's just like the total spin 1/2.
Yes, yeah, and you can change it. There's lots of different examples of these rings that have changed out different metal ions, different spin states, but in each case it's delocalized.
And then a related question: when you were analyzing the pulse dipolar data, the RHYTHMI, did you take into account the size of this cluster? Because this is certainly not a point dipole.
Yeah, so our orientation-dependent algorithm takes into account the distribution of the spin density on our centers. So it was modeled as 8 points of distributed spin density across when we looked at our simulations for all of these. So these aren't, well, they're fits, but they're simulated fits. So they're the library of simulated compounds, and yeah, the spin density is explicitly taken into consideration there.
Okay,
wouldn't that, I mean, just in that regards, wouldn't those ones relax each other like rather fast because they're all dipolar coupled? So then did you do it purposely to have them all clustered together so that they have a shorter T2?
Did we do what on purpose?
The chromium, the clusters, what Maxime was asking about.
Yeah.
They're all
Yeah.
clustered in an area, so it means they're all dipolar coupled to each other as well, right?
Each individual ion.
Yeah.
Yeah, but they behave in how we're looking at it. It behaves as a single spin half system.
I think they're strongly coupled, so they all together behave as if
they're antiferromagnetically coupled around the ring to give this spin half ground state. Yeah.
All right, gotcha. Okay, great. Thank you, Maxime. Any other questions? Please ask away. Oh, yes. Oh, there was somebody. All right. Never mind then. Quick question. So when you did the study, you did the study with rhythmy, which I suppose makes sense because they are fast relaxing with each other, the individual spins. But then I have a question in regards to the orientation selection. Wouldn't that, which one is it? The copper spin? Wouldn't that cause a lot of flexibility, which you already showed in your model that it can take multiple states? Is that correct or not?
Flexibility where?
The linker would allow a lot of flexibility.
Yeah, so that's why we built this model originally, because we were a bit worried that because if you had massive flexibility then that interqubit interaction isn't very well defined. But from the dipolar data coupled with this dihedral bond angle analysis that we did, that at the freezing point of the solvent is actually only a really small. The bond angle that it can actually move around is actually really quite small, and you get this really sort of rigid structure at the temperatures at which we do the experiments. I mean, in solution, it could be a different story, but realistically, we're not going to do any of these quantum computing at room temperature just yet.
Oh, that's fair. That's fair. It's just very fascinating that it actually becomes so solid that you don't have a random distribution. It's just
I think we need to think about the structure I have here of the molecule is quite scaled back. The ring is quite a bulky group. I think if you cared enough to do some good molecular dynamic simulations, I think you would sort of see why maybe it's really not moving around as much as you might expect.
Okay, I got you. Awesome. I mean, that's kind of interesting though too. Like let's say you do the experiments at a different temperature, would you actually see the freezing point? Would you see at what point actually it loses the flexibility? Like, because you said this structure, what you're seeing right now, as you go lower on temperature, it becomes more rigid for that sake, or you have isolated conformation. Is that correct to assume? So if you're at a higher temperature, you would have more different rotamers. Is that okay? Is that what you mean? Hello? You're stuck. Sorry, you were stuck.
Oh, sorry. Can you hear me now? Yeah.
Okay. What did I say? Oh, yeah. So what is it correct? What you're saying is that the linker, as let's say you go for, I don't know, 150, 200 Kelvin, you go down to 10 Kelvin or 2 Kelvin. So inertia allows a little bit flexibility. You have an X amount of rotamers, and as you decrease more and more and more, it becomes rather rigid and increase in rigidity. And would one be able to actually find the point of rigidity when it's actually introduced, or is it just a slow process? Or is there like a point?
Well, I guess it's mainly based on the freezing point of the solvent mix that you use in this. But we did do DEAR between the copper and the nitroxide at 50 Kelvin. And it was evident from that alone that there was a little bit more flexibility in the length of the linker. It was the interactions between the copper and the nitroxide were less.
Right. You're gone again.
We have these really, really well-defined higher frequency components to the trace when we're looking at the XY position of the copper.
Got you. Interesting.
Can I ask one more question?
Please, Maxime, ask away.
In relation to this discussion, when you were analyzing the flexibility of this linker, how did you get the dihedral potentials here?
This here on the bottom left?
Well, the energy dependence on the dihedral angle, yeah. So do you take them from DFT or from some
Yeah, sorry. So these were
libraries?
These were
Okay.
DFT calculations on these fragments here. So I just broke the molecule down into in and around the fragments of the, so.
Mhm.
Okay. Maxime, you're, well, sorry.
Yeah, I'm satisfied. Like I
Okay.
thought it was taken from some force field, but like this, it's probably even better. I mean, it of course depends a little bit on the level of DFT.
Yes,
And you
of course.
probably were also, like when you were computing the entire structure, you were probably also analyzing other clashes, which are outside of these small fragments.
Yeah, I mean, the DF, as you can see on the right, the model that we use to build our library of simulated traces are based on these sort of cone models here. And the DFT was just sort of to guide that. Like, so we did have a look at sampling a very big conformational space, but we were able to narrow that down based on both the fits not being that great and the DFT suggesting that there's really only a small bit of moving around that the.
So at the end, you had this conical rotation model, basically. Or it was still the distribution of the hydral angles.
Of simulated traces.
I'm sorry, I think I did not get exactly. So you checked it with the hydral angle, but then you simplified the model to this like conical rotations, or what did you say?
Yeah, it's effectively the DFT was guiding us, but the conical model is basically so we sample enough of the space to see if there is another conformation in there that hasn't been picked up by the DFT effectively. We wanted to sample a wide enough space to make sure we weren't missing anything.
Okay, thank you.
Great. Thanks, Maxime, again. All right. Ciarán, I think you're breaking off once in a while. It's sometimes very tough. But anybody else have any questions, please? Wow. All right. Well, why don't we just conclude that for today? And thank you, Ciarán, for the great talk. Actually, it's quite fascinating that one can use like a triangle and then have them all couple to each other and actually fully characterize the entire system, which is pretty nifty and cool. I'm actually more fascinated by the freezing option. But anyways, thank you very much. And most importantly, thank you for everybody for attending the talk. And I hopefully see you guys in 2 weeks from now. Oh, actually, no, then Thanksgiving. We're skipping for Thanksgiving. Thank you, everybody. Bye, everybody. See you next time. Thank you, Ciarán.